Just so hello everyone. Today you have another Brazilian colleague here. It's an honor to have him here. Ricardo is a remote sensing scientist. Nowadays he's a postdoc at UCLA and GPL. He has expertise in conducting quantitative research with high resolution satellite images and also LiDAR, airborne LiDAR data, as well as on methods such as deep learning, convolutional networks, neural networks. His current projects consist in studying tropical forest degradation. And welcome, Ricardo. This is a pleasure to have you here. Thank you very much. And the floor is yours. Thank you.
Thank you for the invite, Sibeli. So how many people do we have there today?
Here we have 4 now, but there are more coming.
All right.
And we have someone's, I don't know, in the internet. I must figure out how many we have there. We have 15 online as well.
Cool.
So, thank you.
Well, let's hope I give something useful for you to think about or maybe collaborate. Okay, let me share my screen. Is it this one? Then I put on whole screen. Can you see my whole screen?
Yes, we can.
Okay.
Thank you.
Okay, good. Okay, so my name is Ricardo Dallagnol. I am a postdoc researcher here at UCLA. I'm also associated with JPL NASA. I'm working with Dr. Sasan Sachi here, essentially working with mapping forest degradation in tropical forests, as Sibeli said. And my main work is using planet imagery, so high resolution, around 3 to 5 meters, with deep learning to map degradation. The talk will revolve around deep learning with remote sensing in general, because that's the more recent focus that I have been given to my work and collaborations. So it's a pleasure to show a bit of my recent work, also to talk about other people's works, lessons that we have learned, and also some opportunities. I'll also talk a bit about show some current results. So I don't know if there are people that works in tropical forests as well in the group, but if you have some, perhaps that can give some idea or maybe even some collaboration. So the outline for the talk, I hope that by the end of the talk you can get an introduction of deep learning. If you're not used to it, you don't know what's that. I will show some applications of remote sensing with deep learning, both from my experience and some other papers. I will talk a bit about the challenges, opportunities. I don't know if we have more early career people than me in the call. But if so, I think there are some interesting points for you to think about while studying master's or PhD, etc. And by the end, if you want to ask questions, just shoot and we can discuss. So to start, a very brief description of a neural network and why is that important. So I won't go much in technical details. I don't work actually in developing like the mathematical models of neural networks. I work mostly on applications. So the majority of the talk will be about applications. So the convolutional neural networks, CNN, as you see in the papers, they are the state-of-the-art methods for image segmentation. And that means going from one image. This is the case for, I think it was like Worldview 2 with about 0.5 meter resolution. where we want to map, for example, some tree species that we can see on this image, and we want to get a map of the tree crowns. So this is image segmentation. And this is an example from a paper that we published 2 years ago about mapping palm trees in the very high resolution imagery in the middle of the Amazon. So this is not palm oil, there's a lot of papers going on about palm oil, where you have like plantations of oil side by side. This is palm trees in the middle of the forest. So it's usually natural palms, but maybe created by humans as well. And the novelty about the convolutional neural networks is essentially the convolution, which is the process of sliding a window across an image. So imagine this is the image in the bottom, and this is this window that you do this convolution, and what the model learns with that, instead of, imagine if you had only one value
Can
in
I
this
pause
matrix.
you for 1 minute, Ricardo?
Yeah.
I'm sorry, your audio is breaking up a little bit, and I think it might be your microphone, because sometimes it gets better when you move a little farther away, and sometimes it gets worse. Do you either have an alternative microphone, or could you maybe try moving away from your mic a little bit? We're just getting some static.
Okay. Let me see. Yeah, I got this headset last week. I didn't test it much. I can try to put on my microphone from the webcam.
I think let's try that. It might work better.
Okay. I think right now I'm talking from the webcam. Is it better?
That's a lot clearer from our end.
Okay, good.
Yeah, thank you. We were having just a hard time understanding you. If you wouldn't mind going back just a little bit,
Sure.
because it was breaking up, and I think we didn't really catch your intro as much as you would like us to.
Okay, good.
Thank you. Thank you. I think you're all set now.
Okay, thank you. So the convolutional neural networks, as I was saying, the CNN, they are the state-of-the-art methods for image segmentation. So if you want to start with an image as a very high resolution image from world view to satellite, for example, here, and you want to map palm trees in the canopy of this natural forest, this will be the output, this mask, palm mask. This would be an image segmentation. There's other kinds of tasks that you can do with a neural network, but image segmentation is usually what we want for remote sensing, to have the pixel by pixel mask of the object that we want to map. And this is an example from this paper that in 2020, where we mapped palm trees in the middle of the forest in the Amazon. And this can be interesting to know where you may find this natural distribution of species to explore the ecology of that, or maybe you want to know where there are more frequency of these species to exploit non-wood products, for example. So this is an interesting use of this method. And the novelty about the convolutional neural networks is essentially the convolution. So you may think that this in the bottom is the image that you are studying, and this on the top is this is a sliding window that you go across your image, doing some kind of multiplication, for example. If you think about a more traditional machine learning method, you would have, for example, one value here multiplying your image to arrive at a map. So, for example, if you multiply that the value that you have in the image by a certain weight, certain value, you get an output. But here we multiply the image by a window that looks over the whole image. And what this does essentially, it's able to capture the spatial patterns that you have in the image. And this is really the novelty about this kind of method. And so here's a very simple example of some filters. This is not a CNN, but it's just some simple filters that
If you multiply this filter over this image, you get some horizontal lines. If you multiply this filter by this image, you get some vertical lines. And imagine you combine those two and you get this robot here. But the question here is, what if you don't know which filters, like which windows, which matrices of this you need to use, and which features, like which bands of your satellite image are important for the task. So learning which are the filters that you need to apply and what are the important features is what the CNNs they learn while training. And this is the most novelty about this kind of method. So they essentially they learn those filters that to produce the results that you want. So you have training data that you label yourself, saying this is a palm tree, or this is a house, a building, or something. And the model learns those filters that will arrive you at the map that you want to get. And here are some examples showing what happens in between this kind of network. So you start with an original input. In this case, it's just a number 4 in an image, and the model here on each layer, it creates new representations of this original image, and it goes further. When you go further into the model, it starts to create abstract representations of that image, up to a point that you arrive, for example, at just a vector in here, saying this is the more, it has more probability to be the number 4, for example. But there's also gray values saying, oh, there's a small probability, maybe it's a 6. But anyway, and what we do with images, we have more or less this kind of representations, and very simple representation in the middle of these models, for example, over here. But for images, for remote sensing, we then reconstruct these representations like upsampling. So increasing the resolution again, going finer and finer, up to when we get a mask that has the same input as the original image. So we get pixel by pixel mask of the object that we want to map. By doing that and applying that kind of model over a large landscape, for example, here it's like 10 kilometers on this scale. So you imagine you can have like 100 kilometers with very high resolution imagery. And we mapped the palm trees over this landscape. There are some locations that we see there are more palm trees on the landscape. There are some palm trees that distribute along the terrain or around the cliffs. There are some increased distribution, if I remember correctly, around some rivers, around some places that human beings could be there and favored the distribution of these plants. So this, you can see that this can be useful to study ecology, impacts of human disturbance, and this kind of stuff. And there is this sentence that I like to say, that if you can see it, deep learning can map it. So for example, here in the main image below, we can see this palm tree, and the polygon around it was the polygon that the model found the palm tree. So if you can see it, deep learning could actually add, probably map it, but it's usually it works. So if you're not from, if you don't know much about the different tasks that this kind of model can do, it can do image classification, and don't confuse that with semantic segmentation. Usually in remote sense we do this, but for computer science, people call this image classification. For a given image, you would say this has person, tree, grass, or sky. This can be also useful for remote sensing if you want just to do a very simple classification. Let's say this image has clouds. And if that's enough for you to like filter some images, that this model is much quicker to run than this model. So you may think about doing image classification. There's also object classification, where the target of the model is to create these bounding boxes around the targets. So in this case, where the people, the persons, you want to create these bounding boxes. But usually for remote sensing, we aim at semantic segmentation, that is creating a pixel by pixel mask around, over the objects that we want to map. And in this case, it was a multi-label classification. So there's more than one class here, person, trees or something. And there's also a new level of this kind of classification segmentation, which is called instance segmentation, which is it's more complex to do, and usually much more harder to do as well. You want to classify between different occurrences, different instances of the object that you want to map. So person number 1, number 2, number 3, number 4, and sometimes it gets just clustered here, and it may be a mess to do this. And why this may be important? Because if we go back here, for example, if you want to just map palm cover, so the percentage of palm cover, a image semantic segmentation model is fine. You just have palm or no palm on your mask. But if you want to get the number of palms in this image, the ideal model would be instance segmentation, when you can differentiate between palm trees that occur very close to each other. And this applies also to, for example, buildings in urban environments. You want to be able to say, this is building number 1, this is number 2, even though they occur very close to each other. And I will show an example of that as well. So it's more a general slide talking about we have a lot of data, and it can be used to map different stuffs in urban environments, such as buildings, green area, also to help with natural disasters, map vulnerability. In rural areas or more undisturbed, like you can map forests, you can do tree count, you can calculate disturbance, you can map crop types. So there's a lot of potential to work with the markets as well, not only academics. So like it's about price of properties, making cities more sustainable. Carbon credits is a huge industry right now, and also insurance, especially for crops. And this is also a nice slide talking that saying that AI is the new electricity. Andrew Ng is a big name in AI. So artificial intelligence is present in all of our lives. It's on social media, games, now even driving, like Tesla cars, or you can have that in engineering to make designs, to make augmented reality. You cannot go into Amazon website and, okay, does this furniture, it works well in my room, and you can imagine that going to your room. So it's everywhere. And it's also in Earth observation and remote sensing. We see the development, now I just don't remember if it was last year or this year, but Dynamic World from Google, they mapped all the Sentinel-2 images in the catalog. And while having all the images classified may not be essentially useful, but you can leverage the potential to have all those images classified and have like a confidence level of classifying something. Or you can use that as training data to use on new models. So if on this area the model mapped the same pixel as this class for a long period of time, that has a high confidence that that pixel pertains to that class, and you can use that information to train a different model of your interest. So this is a very important topic for deep learning. I will talk about this later, about training data. This is a nice paper that came out in Nature 2020. I also like to give this example because they mapped tree cover in the African Sahara and Sahel. So it was a huge, huge area. And when the trees are isolated, so they are not close together, this means that those are individual trees being mapped, and you can have an estimate of billions of trees on these areas. And this group is also preparing some new papers that I saw in a meeting recently, showing that those trees outside of forest, may correspond up to 30% of the amount of forest. So you can see how this is an important thing to explore, and the deep learning can help us to map this, quantify this, while applying perhaps a more simple algorithm in pixel by pixel may lose these small trees. So this really shows like the potential of deep learning in large scale. And now some more examples that my group worked. So we did this study back in Brazil. A colleague of mine was working for a foundation, and they wanted to go to kind of sell a product to our organization called EBGE, which is like who does the census in the cities. So they wanted a quicker approach to, instead of going to every new house to count to acknowledge the new houses and new buildings. So he built this model to map all the different buildings on a city. And imagine you have different dates, you can just go in and refine this over time and build this kind of maps. Like these are like blueprints of a city that you can take from deep learning. And the model that we built for this is called UNet ID. So it's basically the UNet model. This is the first model that I showed today that has this U shape. But what it did differently, it allowed us to create a border around the objects and try to differentiate the different instances of the objects. Of course, in some places where the threshold between one building and the other is not very clear, or perhaps the model could be further improved, but it's not perfect, not always perfect, but in some cases it really produces objects like we expect, different buildings correctly mapped. And yeah, this, you can take a look at this paper and apply the model yourself for urban environments. This is another application, a paper that I led, was published this year in remote sensing, ecology, and conservation. So we had this amazing airborne LiDAR data set for the Brazilian Amazon, which is open, by the way. It still doesn't have a platform to easily get, but if you talk to if you send a message to me, I can direct you to the person that leads the data collection. And each of these lines in the middle of the Brazilian Amazon is a transect of 15 kilometers and 500 meters. So it's a long strip. And what I did here, I sampled around 7,000 palms in the middle of the canopy, and I trained this UNet model to map them. And the result was more than 1 million palm trees mapped over all of these locations. And when we extract just one, for example, it looks like this. You can clearly see the shape of the leaves. And if there's someone from ecology and know about plants here, would be crazy about, okay, but then what's this species? And let's dive in about that. But in this paper, we went just a little bit more careful. Just let's make an estimate about palm cover. So we saw that in the Brazilian Amazon, there were areas with much higher palm cover than other areas. And here, as for instance, is an area that is very threatened with forest degradation, disturbance, and this may be one of the reasons that this forest has more palm trees, but also because we see that these regions, they have much lower canopy, shorter canopy, and perhaps that's why the palms can reach the canopy and we can map them. So there's a lot to explore here, but I really like this map showing, like quantifying the number, percentage of palms in the forest. This is a really new way to look at this kind of data. And this is just some quick plots that I did last month for a colleague. I extracted the palm segments for a few trees and sent her. She's an ecologist that works in Brazil. We are interested in trying to see if we can distinguish different species. So for example, this is a more tall tree with leaves that go more up. Perhaps this is a different species that is more shorter palm that has a more wide tree crown. So I don't know much about this part of species, but we plan to do some field work in the Amazon and visit some of these trees and hopefully connect the field and the image, these images, and try to arrive at some species detection. This is a different approach that we published 2020. So José Braga led this work about mapping all the trees in the forest. So mapping individual trees in the forest is not something new, but it's also something that's not yet resolved. It's so difficult to look at an image like this on the top right and draw every single tree. If we give this to the 15 people that we have in the room today, and everyone draw all the trees in this one tile, and then we compare, it will be a mess because it's not simple to do that. Some tree crowns are just hard to find where is the limit, and so we took an approach here to try and solve this by building virtual forests. So these are very rough forests that we built here. It's like we got some backgrounds of forest, and then we manually drawn some tree crowns and put on top of it. And the idea behind this is that if you know exactly the limits of these trees, then you can just build this virtual forest, putting tree crowns on top of each other, and you know exactly what are their boundaries, and that would help the model to understand that. And so this is a result from this model on top of this image. For this area that we trained the model, it worked quite well. The issue now is to try and scale that to a different area, and usually it's like that. We didn't go much further with this because the postdoc that was leading this moved to another job, but this deep learning has really potential to solve this issue. There's been new papers on this, so if you're interested about that, you can probably take a look on this paper, see which papers are citing this. This really gets cited in the last year. We are very happy with this. And this is another thing that I was looking recently, maybe a more physical and smart way to simulating this forest. So using radiative transfer models, 3D radiative transfer models, so we can put some properties of the forest that we want to create. And for example, have a forest inventory, you know the location of the trees, you know the tree crowns, and you put in the software to create this very real looking images. Maybe this one to the right, not so much, but this one to the left, they look quite real. And using this new technology to build this virtual forest and then trade the models. I find this quite nice. There's no one from my group using this approach right now, but there's someone from the group that maybe want to pursue this. We can talk and maybe do that. So this is a different model that was published this year. Fabian led this paper where we built essentially a K-mean model. If you are into image processing, you probably know K-means. It's a model to classify clusters of information. In the case of remote sense images, to cluster the pixels in different classes. So you just specify, I want 5 classes, and the model would split the pixels in between these 5 classes according to the spectral information or whatever data you have. So we wanted to make something similar for deep learning that worked not only on the pixel level, but on the image level. So similar to what I was talking about with the window texture information. So this model called K-texture, what it does, it enters a input image. For this case, we tested with planet data at 5-meter resolution, and we start the model with a number of classes. So we put this binary masks for it to try and find. And also we want to find both the binary masks, that's the final goal, but we also want the model to find the textures, because those textures can also be useful to train other models and more do other stuff. But essentially what we want is the binary masks. So, but the model understands both the texture of a different class and the class itself. So if you specify 4 classes, it will return to you image with 4 classes and the texture belonging to those 4 classes. So here's a more clear example of the result. So in this case, we specify 2 classes, and we want to get forest and non-forest. So this is the original image from Planet, and this is on B, it's the class binary map of forest, non-forest. On the C is just non-forest, on D it's just the forest. So one thing that I take from this is, usually when you apply a pixel by pixel classification for tree cover, forest cover, usually dark pixels, perhaps it may confuse to something else, or perhaps the most bright pixels, they could confuse to something else. But since the model looks at texture, contextual information, and not just the pixel, it's able to find these homogeneous regions, these forest fragments quite well, because they have this texture that are different, for example, on a forest, here on the forest, that's different from the pasture that's just to the side. It's still green, it still have very likely very high near infrared signal, but it's not a forest. It doesn't have the same texture. The interleaving crowns and shadows creating this representation of this texture that we associate with a forest. So here's on another approach also with forests. This is a paper that I published in 2019. This one didn't use deep learning yet. I used random forests, a machine learning model. So it's essentially decision trees. So for every pixel you look at the value, you say, oh, is it higher than this or lower than that? You have like some groups, and it does like a big set of that. And for this paper, we wanted to map tree loss with very high resolution imagery using LiDAR as a reference for that, because LiDAR is just amazing. LiDAR can, between one image to another, if you calculate the difference with LiDAR, we already got our result. It's this area and this area you have tree loss because the height changed a lot. It's a very abrupt difference in height. But with optical imagery, that's not the case. You have shadows, you have phenology, so trees that are green in one image that are leafless in the other, and that affect our estimate. So for this problem, I applied random forest as a first step. We produced some maps showing areas that had more logging than others. We also point out some potential illegal logging outside of these logging concessions. But then more recently, I started to apply deep learning for this kind of problem. And this is one of my ongoing study, paper that I'm writing right now. So we have here, for example, not just logging, but other kind of forest disturbances that lead to forest degradation. So this on first column is logging, where we have, in the middle forest, we have trails, lines, we have decks or patios. So the areas that you open an area to put the timber, to put the wood after you cut it, and you have the gaps inside the forest where you fell the tree, it falls down, opens a gap. And you can see that on planet imagery. The kind of sample that I created over this image are these in blue. So not only the features like the trails or the gaps or the decks, but I wanted to map the whole area. And here is some example of the prediction for this example. In this project, I'm also interested in mapping fire, because in the tropical forest, especially in the Amazon, we have the most disturbance that cause degradation are logging and fire. So I also wanted to map fire. So you have here different examples of fire that creates this ring-like patterns, fire that burns almost everything to the ground. You have barely no vegetation left. More recent fires, older fires, you have a lot of variability. So I include all of that in my model, and it's able to understand that kind of information, produce these homogeneous maps. And I also include the roads, because roads, although a road is essentially a deforestation, but linear, I don't know. But roads leads to more deforestation, lead to more degradation. So it's an interesting disturbance to be mapped. And here are some results, preliminary results from one example in Mato Grosso state. So Mato Grosso, just as a reference, is one of the hotspots of degradation in the Brazilian Amazon. It has about 50% of the logging and fire, according to previous studies. So we have here, for example, the result of my model on the top left. On the top right, we have the product from Hansen, Global Forest Change. In the bottom right, we have the Tropical Moist Forest from the European agency, JRC. And on the bottom left, we have a reference for logging, which is one of the official data from Mato Grosso based on paperwork, like permits that people ask to log the areas. So these are not only legal logging, these are also legal logging, and also visual interpretation of Landsat imagery. So you can see, looking at this, that the results that from our new model, it maps the areas more comprehensively, more homogeneously than the other models. What the models from GFC, TMF, they usually map the areas that more fully go from a tree to a bare soil. So that's why they capture mostly the roads, the logging decks, and not so much like the real extent of the logged forest. Um, and I can imagine that if you want to estimate how much forest has been logged, having the area is more important. That's my perspective to that. And also, these two products, they are not products directed to logging. They are forest disturbances or forest degradation in case of TMF. So they also map fire. So they in this case, they do not yet disentangle these kind of effects. So for example, here, there's logging, but in here, it's not really logging. We can see on this next slide that in our model, we capture this as fire. It was also mapped by GFC, perhaps even better than logging itself. And here's an example of another fire burn scar product from Map Biomass from Brazil. It also maps this area. And just as a comparison, this is an area that burned in December 2017. You can see this area was burned, and the boundaries of this burned area was picked by our model like very homogeneously. So this is more about the power of this kind of deep learning models. Here very quickly the result of roads. I didn't compare to other data sets here just to show roads in the middle of forests or in this neighbor boundaries of forests. And this is another result I got this month comparing these products. So I compared all these products available to a common reference based on planet visual interpretation. And the result about that is that our study obtained a slightly higher F1 score, which is, you can translate that to the agreement between the map and the reference, but only looking at the presence of the class that you want, only at the predictions. So you do not consider in this estimate the absence of your class, because if you do that, if you make a map that's entirely zero, you don't have any disturbance, you probably get a very high accuracy. So usually in deep learning, you use this kind of metrics, F1 score or other similar metrics. So we obtain similar metrics to the official data sets from Brazil. CIMEX is the one I showed before. Also DETER, the one from the National Institute for Space Research, INPE. Both of these are made visually, manually, and they have a good agreement with our product. And I did not use those data in any way to make the training data or validation. And they also agreed for forest fire. And here, one interesting thing is that most of the fire products, they do not match well with the reference, because in my perception, they map mostly deforestation fire or fire related to croplands clearing and that stuff. So we have a lot to advance still to map really to map well forest fires and degradation. I think I'm coming to the end of the hour, so I'm going to speed up through some of these slides that just showed large scale what the results look like. We'll skip this one. And yeah, just an overall message about this, that we have a lot of new research about new models, but I think we as a remote sensing Earth observation community, we can focus on applications, building new applications, not necessarily new models, but new applications. And the main issue about that is not to have the data anymore, but having the knowledge and the training data to make this happen. I will skip a few slides here. And here's an important thing, how to collect labels to run models. You can do that visually, delineating, vectorizing. That takes a long time. Usually for deep learning, you need to make a full sample of the areas that you want to map. So this is forest, and the rest is whatever else. Or if it's a multi-class map classification, you need to map for all of the area. It's called dense label. So make a label for the whole area. But there are also some initiatives that leverage what they call weak label, perhaps just a point, just a pixel. I still did not use this, but I think we need to take a look on this to really improve. Here's a good repository for deep learning applications with Earth observation, satellite images. So take a screenshot of this, take a look afterwards in this really good repository. There's a lot of applications here: landslides, glaciers, solar panels. Yeah. There are also some initiatives sharing training data sets for land cover. This is one of those. I also mentioned the dynamic world that can be used for that. Here's a call about CPU and GPUs. I feel I need to always say about this because we don't, as non-computer people, usually we don't know what's a GPU. I don't know. So GPU is what we need GPUs for deep learning. And it's like having a truck that can carry a lot of data at the same time compared to a very fast car, which is our CPU. So we can have that in local machines, but they are usually expensive, or they were, because the crypto market is actually crashing right now. So if you want to buy some cheaper GPUs, the time is right now. So some RTX 3090 is going for under $1,000. So that's pretty cheap for the previous prices. You can make a very good computer, or you need to move to the cloud. So recently I have been working with Amazon Web Services, where you can have machines with like 1 GPU, 4 GPUs, 8 GPUs. You can have big machines to scale the processing that you need to arrive at the predictions that you want. So to make a prediction for one jurisdiction, one city, one state, perhaps it's enough to do on a local machine. But if you want to go on a larger scale, you need to look into that. And this is more for the early career people. I like to say this, that if you want to really work in Earth observation remote sense, you need to learn programming. You need to know about GIS. It's imperative that you know how to visualize data, but it's also imperative that you learn programming. So R and Python are probably the most top ones. And independent of which one you use, learn about GDAL library, which is a lifesaver. It can work with huge data loads, and I use it like not every day, but every week. Here are some more references. I really like this book. There's also a version for Python. You can really learn. There are examples to follow, and you can really learn to apply the models. And I like also this review paper that gives you a perspective about deep learning. There's also this material that I made last year for some short courses in Brazil. If you want to take a look on that, there's a class showing this example in Google Colab. And oh well, that's it. I talked for about 50 minutes. Thank you for listening to all of that. If you want to contact me, there's my email, there's my Twitter. Yeah, if we have time for questions yet, let's go.
Thank you, Ricardo. Thank you very much. That's great. So I'd like to know if someone has any question. Have you heard her? The
No.
question? Nope. Can you come here? And yeah, maybe you can ask here. We are switching. I don't think so. Yeah, maybe you can come here. Come here. Yeah, I can repeat it if you want. She would like, yeah, come in, come in, come in.
Don't be shy.
Yeah. Don't be shy.
Can you hear me now?
Yes.
Okay, thank you for your talk. A lot of problems that you spoke about was the CNN and the unit for classification based problems. Have you looked at any regression type problems?
Good. It's a good point. I'm not. I never myself used regression with deep learning, but I am in my group recently. We are using deep learning to make height maps based on different predictors and using like JEDI, for example, as a reference data for height. The challenge, it's a huge challenge to do that because it's sparse labels. It's like the example I showed, you have just like one point, but it usually works better if you have like a whole image of data to make the training. So that's one issue, the sparse labels. Perhaps for airborne LiDAR that works better. But my perception so far is that more traditional machine learning models, it does pretty close to what deep learning does for regression. Maybe someone can change my mind, but for now, I think it's much better for image segmentation than it is for regression.
Okay,
Great.
and I have one last question.
Go ahead.
You said hard clustering in one of your slides. What is hard clustering compared to just regular clustering?
I think you were mentioning for the K texture paper.
Yes.
Okay. To be honest, I don't know 100% the answer to that. I think it's a matter of if you have a probability of the pixel belonging to a cluster, and what the K texture does, it tries to really like nail down. This is this class or this is that class. In the end, it doesn't output the probability. It's just separate between clusters. I think it's that, but I need to take it, go into the paper again and remember that.
Okay, thank you.
Thank you, Ricardo. Someone, yeah, Jennifer, I don't know, from the internet, wanna?
Yeah, I have a question. Can you
Yeah,
hear
go
me?
ahead.
Thank you so much for your wonderful talk, Ricardo. So I've spent about a decade of my career studying fires in Mato Grosso state and a
Wow.
large-scale burn experiment. And one thing that I have thought of that I don't think I've seen anybody implement is that there's a spatial signal of uncontrolled or unintentional fires, which comes out in their daytime to nighttime progression. And they burn at different intensities and they leave almost like these rings of based on the mortality of trees that happens based on different intensity levels. And we had a paper, in fact, some of the folks on this call participated in that and are contributing authors, but the daytime and nighttime detections from GOES could potentially offer a way to delineate between the deforestation fires and the management fires that are happening on pastures using this daytime nighttime signal. So coupled with the image classification, there could be another source of information that would help to supplement that. And this is just like planting the seed of an idea. But I would love to see somebody leverage that information to help delineate the unintended fires.
Oh, that's very cool. I think I read that paper before. At least one of them. There's more than one. But what do you mean? What is the essential difference between the fire burning in the day or the night?
The signal comes through in terms of how vegetation responds. So there's a different intensity that happens as a function of different temperatures and relative humidities during the day versus the night. And you actually can see that the patterning is really stark. I've seen it in Landsat imagery in Mato Grosso, for Mato Grosso state, where you can see that these rings essentially is what they look like, and based on the intensity differences and then how the tree mortality is different across that daytime to nighttime cycle. And I could send you a couple of things too if you want to move on to some other questions. But
Cool.
I loved
That
your
would be
talk.
helpful. Yep.
And it was so great to hear what you're up to and how far the science has come on detecting deforestation and land degradation in tropical forests. It's amazing.
Oh, thank you. If you send me that, I'll be very happy to take a look.
Great. I guess we're almost on the top of the hour. Yeah, Max, go ahead.
Yeah, hey, Ricardo, thanks. Great talk. Can you talk a little more about how you're thinking about the time dimension in the degradation project? I noticed you had like predictions for each year. Are you applying your model to annual imagery separately for each year, or is time like in the model somehow?
Cool. That's a very good question. In the beginning of the project, the idea was to do change detection between one image to another. But when I started just testing it, predicting on different dates, I realized that a more simple approach of just taking a look on the difference between the images was enough to arrive at to get new areas. So I kind of left the change detection behind for a bit. But I think the change detection, looking at two images at once, like every two images or three or more, will be important to get the recurrence of fire, because then we can see if there is a change or a more negative change, like a new fire. But for now, I just apply the model over all the images. I have one image every 6 months in the beginning of the time series. So it's a biannual data set. And in the end of data set, after September 2020, until nowadays, I have monthly data. So what I did essentially, I applied the model for all the dates, and then I aggregate the data in 6 months. So those monthly images of the recent period, they may be more cloudy because they're monthly and not a 6-month composite. So they essentially have more clouds. So when I aggregate, I made like a rule saying that the model must find more than once the disturbance in order to be characterized as a disturbance. So that way I clean some of the false positives and arrive at a more clean product. So that's the way I'm doing right now. If you have some suggestions for including better the time in a further product, I would be glad to discuss that as well. I never use I just use this one like a Siamese deep learning network that compares two images, but maybe there's more interesting models.
Awesome, thank you.
So I guess we are on time. So thank you very much, Ricardo, for being here. I guess everyone here enjoyed it, like some insights for our project as well. And I have some questions as well, but I will follow up by mail with you. Thank you very much for being here. So yeah, have a great day, everyone. Thank you.
Thank you very much.